So I want to create a representative volume element for a unidirectional composite. And someone suggested that all I need to do is to make sure that I have all the fibers within the RVE. Another person suggested that maybe that's not the right thing to do. Why not have some of the fibers on the edge and some inside the domain? What is the decision that I should take? Should I go with option A or option B? This is a question that we're going to explore in this video and see the influence of these choices in terms of the yield stress, the elastic properties, the damage evolution, and the energy absorption on the domain. So stick around to the end and find answers to all of these questions. Let's sit back and relax as we get started with this modeling. So as we look into this question, we are going to follow a first-year PhD student called Stephen. And he's dealing with this conundrum of how do I actually generate the effective properties of a unidirectional composite, especially whether I have fibers located inside or outside the representative volume element that I've chosen. And so he's dealing with this question and he wants to find a solution to it. And so he comes in contact with one of the postdoctoral researchers in the group, and he says all you need to do is you create a domain, make sure all the fibers are located within the RVE, and that's fine, and then you run your simulations on that. But then he decided to take a second opinion, and so he goes to another postdoctoral researcher who explains also to him that you can also create your representative element, but make sure you have some fibers on the edges. And so Stephen is a bit unsure as to what to do, and so he decided, okay, I'm going to test these ideas out. The first thing he wants to do is to create two representative volume elements according to each of these guys that have advised him on what to do. So we have a large representative volume element and a small representative volume element. The large representative volume element will be of size 120 by 120. The fiber will have a diameter of 15 microns. The smaller representative volume element will have a dimension of 45 by 45 with exactly the same fiber diameter. So he goes ahead to build the representative volume element for these systems. One, for the small case, there will be fibers on the edge and fibers not on the edge. And for the large one, the same thing, fibers on the edge and fibers not on the edge. Incidentally, Stephen has access to software called PBCGen, which will help him implement periodic boundary condition on the domain, and MontCarlGen2D, which is again another code that Stephen has access to help him create random distribution of inclusions within the domain. By the way, if you want to have this software that Stephen is using in creating this model, please look in the description section of this video for links that will help you download the MontCarlGen or the PBCGen software that he's using even in this model. One thing that Stephen really wants to do is to make sure that he has periodic boundary condition implemented in the domain, because that will give him as close to reality a prediction as possible. So we're going to look at what Stephen is doing even in the simulation. So let's get into it. So as Stephen begins to look into this problem, he wants to start creating the representative volume element by using MontCarlGen software, which is a MATLAB implementation of the MontCarlo approach to help him with this problem. So let's look at what Stephen is doing. So here we are. This is MATLAB, and what he would like to do here is to create the domain. So within this code, this is the MontCarlGen that will help you create the MontCarlo generated. So if we open this, right click and open as text. So within here, you try. So this is the information that Stephen has access to. So the length of the RVE that he wants to choose is a large RVE size of size 120 by 120. The diameter of the inclusion is 15. And he's working with a volume fraction of 35% for this inclusion. And now the origin of the RVE will be 0 and 0. And incidentally, he wants to model the fiber that is E-glass and the polypropylene, which will be the matrix. So we see that here. And in the end, he wants to create a unidirectional composite. So there are other things that he wants to be aware of. And for example, what is the minimum distance separation between the closest two fibers? And in this case, it's about 5%. And there are these two options within this code, and that's the periodicity of the material and the revised RVE size. So if we put in 0 here, what this means is that we are interested in creating the RVE where the fibers are periodic. So that means they are appearing on the edge of the RVE. And so for this first case, Stephen will put 0. And he chooses not to revise the RVE. The essence of revising the RVE is to make sure you have an accurate, exact volume. So we've got all those things in place. And all you need to then do next is to type in MontCarlGen. So you call this MontCarlGen and then you run it. So if we enter, so what it will do is that it will run and generate all the inclusions, and there are 29 of them here, finishes, and then it instantly will give us this result. So this is the result that shows the distribution of the inclusions with a volume fraction of 35%, about 35% approximately, and the sizes are all there, and the fiber inclusions appearing on the edge. So this becomes his first RVE, which we'll call the large RVE on the edge. So he decides to think about, what if I decide to obey the other postdoc that suggested that what I need to do is to have no fibers on the edge? So how would he do that? So again, everything will appear exactly the way it is, except that when you get to periodicity of material, that changes to 1. So that means you want everything to be inside there, non-periodic. And then he does that. He calls the same code again. It will run through the same number of inclusions. Now, in this instance, the fibers are not appearing on the edge. So this means everything is locking inside the RVE. So it will be interesting at the end to see which of these will give you the better result. And this is the answer that we want to explore in this study. Interestingly, Stephen also wants to look at a smaller RVE type and see whether there's an influence of really using a smaller RVE type. And this influence of edge fibers, would there be a problem? So we're going to go back to the same code. So now we're going to switch this RVE length to 45 and 45, which is 3 times the fiber diameter. Now everything remains exactly the same. So we'll go back and make this 0, which case you're looking at a system that has periodicity of fibers, which means the fibers appearing on the edge. So he will call again that MontCarlGen system, and MontCarlGen will generate and give him a result like this. So this is a typical result that he can generate for this setup. Okay. So you can see the fibers appearing on the edge. If you run the same system again, you got another distribution. Now we go back, change the system from a periodic material case to now one where you don't want any periodicity of material, in which case no fiber appearing on the edge, everything will be inside. And then he will run the same system again, still with MontCarlGen2D. And now you get a brilliant system with nothing appearing on the edge. So he has 4 represent volume element type that obey the objective that he wants to. So if we look inside this code, you see there are 2 examples of folders containing the information that he wants. So let's look at the large RVE case. So within the large RVE case, we've got case 1 and case 2. Case 1 being with the fibers on the edge and case 2 being fibers not on the edge. So if you open that, then you get a few information that are there, for example, the RVE. But the most important thing that he wants is actually how to take this information from MATLAB into Abacus. So let's look at that. So there is a Python script that comes with MontCarlGen, which is the software that Stephen is using. If you open this script, then you find that there is a set of Python scripts that are already available for him to use as part of his setup. So he's going to use this to run his simulation, and this will apply in all cases, even for the large ones and the small ones. Now the next level is to go into Abacus and see what simulation result he will generate. Right here we can see that these are the Python scripts, rename them. So basically simulation 1 will be for the small RVE edge and all that. If we just have a look at what this will look actually. So this is a text-based representation of the system. So again, right at the top, you've got a little bit of introduction, and this is exactly written by MontCarlGen for Stephen. So some import information, and then you can go into what the Python script is doing. And this basically is the instruction that Abacus has to work with in creating the domain. So what we're going to do, we're going to start with the first case. So we just go Control A to select or Control C to copy. So we now move to Abacus. So within Abacus now, he can bring this information in. So right at the base here, in this kernel command system, he will paste this code. And what this code will do is basically to recreate the domain. So this is one of the domain that he's created. So the fibers are appearing on the edge. Then we can go back and take the next one. So the small RV with no edge, we'll copy Control A and Control C to copy, and then go back to the base and paste. So this will create the second case where there is no fiber within the system on the edge. So that's for the small cases. So we'll go to the third case, which is here. So Control A to select all and Control C to copy, and then go back into Abacus and we paste that information. So again, this will run through and generate the result for the large case with the fibers on the edge. And finally, we'll go to the third case, select all, Control C, go back to Abacus and paste it in that kernel command. So that will create all the fibers. So it's got all these different names associated with them. So now Stephen has created all 4 represent volume elements inside Abacus. So this is sort of result that he gets. So basically we've got the large representative volume elements, the edge and no edge, and the small representative volume element, the edge and no edge cases. So they were renamed from how they initially were imported from MontCarlGen. So if you open that, there are three parts: the fiber and the matrix parts, and then the combined system, which is what you see here. So the first thing Stephen needs to do is to do a section assignment. So if you double click here and click on the matrix, so the matrix will need to be associated with the matrix section, which is polypropylene, and then you can select everything, double click on the matrix, leaving the fiber behind, and then this becomes the fiber case. So this gives you a way of getting that, and then you can switch on back into materials, and that tells you exactly that the assignments have been all properly done. Now he needs to create some nodal sets that he will use to extract the behavior of the system. So if you double click on the sets, so we're going to call it the corner nodes, and that's by pressing down shift you can select the edges. Stephen will need to select the edges of the domain. So these are the four corner nodes that he's going to use to extract the properties of the system, and then click done. So the next thing he needs to do is to mesh the domain. So if we go to the meshing of the domain, so we first need to seed. So 1.35 is acceptable, and we could, okay, if you select that, so triangle free meshing is fine, and then he can go ahead and mesh the domain. So there are some other things that he needs to think about. So for example, from MontCarlGen, the properties of the fiber and the matrix are not given. So it's just a shell that contains that. So for the fiber, the mechanical properties will just be elastic is for E glass. So 73 e to the power 9 and 0.20, it's okay for the elastic properties of the fiber. The polypropylene would have elastoplastic behavior, so the elasticity of the polypropylene will be 1.308 e to the power 9 and 0.40 for the Poisson ratio. And then in terms of the plasticity, so it's going to use plastic softening approach. And so here is the data that tells you that you will need to use, so the yield stress and the plastic strain. So you take that information and then we'll just paste it in here. So that becomes the yield stress and plastic strain for the polypropylene. The polypropylene yields at 40 megapascal. And then we'll finish with that. So he's got that information. The sections have already been created. The assembly are already created from MontCarlGen. We just need to create a step. So we call this a loading step. And this loading step will be a static general is fine. Then there will be a history output that he needs to create to track what's happening. So we're going to call the corner nodes history output. And then basically that will be associated with the corner nodes that he selected initially. And we are going to just look for reaction forces in the 1 and 2 direction, which is X and Y direction. The coordinate position in the 1 and coordinate position in the 2, which is the X and Y positions. And then displacement in 1 and displacement in the 2. So these are typically the information that he wants to track. Then what about the boundary condition? Because he's going to use periodic boundary condition for doing this. So you only have those 4 corner nodes as anchor points that you can use for setting this up. So the initial boundary condition will be X back at the roller. So you will only need to use that point and this point as the anchor point, and it's holding it in the one direction. So we'll do the same for the Y base roller. So this point will be held as well. And then finally, so in the Y direction, and then finally he needs to apply a load. So we're going to call it L tensile load. And it will be associated with a loading step, and this will be applied right on the domain on that point there. So this would have to be for this case, which is 45. So we're going to apply a 30% strain, so that will be 15 micron displacement. So everything is fine here. The meshing is okay, and then the model is ready to set up to run. So what he would then need to do here is to go there, and the models have already been created. He will need to then bring it into another software that will apply periodic boundary condition to the system. So the PBCGen software will be a MATLAB implementation, which looks like this. So basically this is the code, and there's a little README file that you will need to read if you're interested. So what we're going to then do now is we'll copy the link where the code is saved. So copy that link, go back to Abacus, and then we'll make that link our present working directory. So we set that as our present working directory, which is this, and then we can then right click on that case and say write as an input. Then we go back to MATLAB. So you see it appeared here as an input in MATLAB, means that it's now available for us to apply periodic boundary condition onto it. So it's quite straightforward. So you just do PBCGen, and then run it. So there's a bit of information. It asks you to select which input file. We only have one. So we select that. So it will run through. And the first step of what it's going to do is it's going to plot all the nodal coordinates, find which ones are in the X positive phase and the Y X negative phase, and all the intersection. The corner nodes that we're going to be using to apply boundary conditions are all identified. But for periodic boundary condition, we really only need to work with the corner nodes, the boundary nodes. And so this is what is clearly distinguished here. At the end of the simulation, what you will find is that it creates a job folder, and that job folder will be this. And within that job folder, we have an updated input file, which comes from MontCarl PBCGen. So if we look at that updated, so what it basically updates is the original information by creating a set of nodal points like this. And then also later on here, it also creates the stack equation, the constraint equation that imposes periodicity. So it makes an update on the original file that we created, and every other thing remains exactly the same. So what we're going to do is to run this model. So abacus job is equal to, and so we'll put the file name, which is sim. And then we want to see what is going on, so we make it interactive. So that's the command, and we're running this abacus model inside MATLAB, and then click enter. So this will give Stephen the very first set of results that he wants from his simulation. So at the end, what you notice is it will run through the simulation, and once it tells you that the job has been completed, then you know that you're ready. So then you can go and visualize the result. So again, what we'll do, we'll copy that link, and then we go back to Abacus to visualize the result, because we need to be able to visualize the result. So this is basically the first instance. So if we visualize the result, it gives us this sort of result that we're seeing here. So if we change this to plastic strain, so you can see now it's showing you what is going on with this simulation. So basically you've got the fibers as rigid system in this plastic case, and the matrix is plastically deforming, and it's showing, okay, there are fibers on the edges, and you're getting some interesting result. But clearly we don't just want to stop here. We are looking for the effect it will have on plasticity, on yield stress, on post-yield behavior of the system. So what we're going to then do is to do a little bit of probing to check. And luckily for Stephen, he had already asked for certain history variables. So we'll click on these history variables and then move on within this window. So there are the coordinate files we asked for, and then we'll select that, pressing down Control, you select this one, press and drag. So basically we have all the displacement data, the reaction force data, and the coordinate position data, X, Y, Z, and we plot that. So that gives us a full set of all the results we want, but that's not a problem because we're going to iterate on that. So plug in. So what we're going to do, export this data the way it is into Excel, so that we can then do some further manipulation on that to generate the result that we're interested in. So this is the result that we output export. So Control or A to select all, and Control C. So basically we select that, and I've already created an Excel sheet that has been formatted to receive this data. So this is what the Excel sheet basically look like. So we just need to paste that information here. And what is really interesting at the end here, so there is a way to extract the force from the data that we generated. If you're interested in understanding this, look at this video that I've made that talks to you about how generating stress strain data or force displacement data from a PBC enabled domain. And then it also generates the stress and the strain for the system. So we've got all that data, and then it gives us an idea of what the plot will look like. So right at the top here, for this small RV edge that we're looking at, the length was 45 and 45 like we specified. Of course, because it's a 2D system, the height will be 1 unit. So there's also a calculation for the Young's modulus, and that calculation is basically the slope of this elastic region in this data. And then the yield, the effective strength of the yield stress is basically the biggest stress value in this domain, which will be somewhere around here. So that's for what we'll do for the small edge. So this is for the no edge case. Then I've also done the same thing for the no edge case. I've done the same for the large case, and also the same for the large no edge fiber case. So again, the dimensions change and the values are all together. But what really is important is if we can put all that information together to observe what effect it will do. So if we look at the collection of the result, and next time we'll begin to see what's going on here. So basically this is the stress strain data for the simulation. So I'm cutting it off around the 15% strain, because this simulation ran as much as the 30% strain, but nothing was really happening there. So we'll stop it around here. And you could see, okay, this the stress strain plot is comparable, they look alike. But what really is important is when you start looking at the numbers that you see here. So what I've also done is that I've gone to calculate what would the actual transverse modulus be based on the volume fraction and of the fiber and the metrics and their Young's moduli. There is a calculation here. And basically, this is the equation. This Chamis model is what I've used to calculate this transverse modulus for this material. So what we know is that the transverse modulus for this material would be 2.381 kilopascal. So that's fine. The yield strength would have to be limited by the yield strength of the matrix, which is 40 megapascal. So that's what we'll expect. So now when you look into what we are generating from the simulation, so basically the RVE with the edge is coming up at 2.411. And what we actual value is 2.3. So still within that. The large RVE with the edge is 2.46, still comparable to 2.38. However, the no edge cases have very low prediction of the stiffness, and that becomes really interesting. And so what we can first see right away is that if you don't have fibers on the edge, your effective elastic properties, the Young modulus properties of your composite will not be correct. It will be way off than what you will expect when you have fibers on the edge. When you have fibers on the edge, they are quite okay. So there is really not a lot of difference, 2.411 and 2.464. Even for a small RVs, and he's getting a good prediction compared to what is recommended in literature, which is a larger RV, precisely because it's got fibers on the edge. Now, in terms of the effective strength, what we'll expect will be 40. And you can see for the large case, because it's quite a sizable system, so the strength properties are correctly predicted even in both cases, whether you've got fibers on the edge or fibers not on the edge. Okay. However, the strengths are not very well predicted for the smaller RVE with the edge. So this could just be maybe due to the problem of just one simulation you predicted, but clearly there could be other reasons why this is the case. So what really becomes interesting is when you study more what's happening post-yield, because there's a lot of behavior, a difference in behavior for the system. So what I've done now is to look at the system and said, okay, fine, I'm going to just focus on what's happening post-yield. And instantly you begin to see a lot of difference as you zoom in closer into the model data. And the red line here is the small RV with no edge. So that means there's no fiber appearing on the edge. And you could see that, okay, it goes a while, and then the energy dissipation in the post-yield behavior is much, much gradual. Not a lot of energy is being released into the system, because what is happening here is that the area under this graph is the energy absorption in the system. So that's what you see here. And you see the same even for the large RVE size, the energy dissipation also is not very sudden, it's not as gradual. So clearly there is an effect of having fibers not appearing on the edge in terms of what happens in the post-yield behavior and the energy absorption. But when you look at what's happening when the fibers are appearing on the edge, you see a good, almost immediate dissipation of energy. The strain energy is less in this case compared to the other cases. So what is happening here is that fibers on the edge is good for damage evolution. However, when you have fibers that are not on the edge, it's detrimental. It delays the damage evolution. If we have the actual experimental data, you'll find that the data will probably most likely lie along this line. So this delay in dissipation of energy is really as a result of the fact that there are no fibers on the edge. So those are the obvious conclusions that Stephen can arrive at following this simulation. One other key observation from here is that the RVE size is clearly having an influence on our prediction. And so the question is, what would be a good enough sizable RVE for your prediction? If that's the question you want to ask, you do need to look at this video. Thank you for your interest in this channel. Bye-bye.